Hello all, welcome to this video on machine learning. Today I'll be talking about gradient descent algorithm and metrics method for simple and multiple regression. We'll begin with the basics of gradient descent algorithm. Slope is the ratio of altitude change to horizontal distance between any two points in a line. Now this will give us the measure of its steepness and direction. We usually go for the average slope between any two points. For example, considering these 2 points, we have the vertical difference as 24 and horizontal difference as 15. So the average slope will be 24 by 15. In order to find the slope at a point, we usually find the derivative. Now derivative will use the slope formula. From the figure, we see that considering these 2 points, the value of x will change from x to x plus delta x, and the value of y will change from f of x to f of x plus delta x. For example, if we take the function x square and find its derivative, we get it as 2x, which means the rate of change at any point there is 2x. For multiple variables, we'll go for the partial derivative. It is taken with respect to one of the variables by keeping all the others as constant values. Now it gives the rate of change of a function in the direction of a variable. It can determine how changes in the direction of a variable will influence a function. Now consider the multivariable function f of xy, which is given by xy square plus x cube. Now taking the partial derivative with respect to the variable x, which means we keep the constant, that is the other variable y. So we'll get y square plus the derivative of x cube is 3x square. Similarly, we go for the partial derivative with respect to the variable y, which means x is kept as a constant. The answer will be 2yx. Now in a higher dimensional function, gradient is a vector that is made up of all the partial derivatives of the function. In this case, both the partial derivatives of x and y are included in the gradient vector. Now gradient of a function f of xy is represented as inverted delta f of x comma y, giving a column vector just containing two values here, dou f by dou x and dou f by dou y, and we will substitute with the process we just did before. So the values will be y square plus 3x square and 2xy. Now intuitively, a derivative of a function is the slope of the tangent line that gives a rate of change in a given point as shown in the figure here. If the function is higher dimensional, we will have to find the partial derivatives to find the derivative, that is the rate of change of the function at a given point. Now we can consider gradient as a slope in a higher dimensional function. Now the gradient will give us the direction of maximum change and the magnitude indicates the maximum rate of change. The gradient always points in the direction of the steepest increase in the objective function. Now a function that we want to minimize or maximize is called an objective function. When we are minimizing it, we call it the cost function, loss function, or error function. Now when we update the variables or parameters of some cost function in the direction of the negative gradient in an iterative manner to reach the minimum of some cost function, we'll call the process as gradient descent algorithm. On looking into the figure, we'll see that j of theta 0, theta 1 is the cost function here, and theta 0 and theta 1 are the variables or parameters. The idea here is to find the optimal value for these parameters to minimize the cost function, which is done using the gradient descent algorithm. Now let us see this concept in the context of linear regression. Here we need to train the regression model with historic data so that it can predict y with high accuracy. The linear regression works by finding the coefficients of a line that best fit the historical data to predict y. Now we represent this line with the equation y is equal to mx plus b, where m and b are the coefficients or variables of the function. Our task here is to use gradient descent approach to optimize the coefficients of the regression model in such a way that it has less prediction error. Now we'll look into the steps involved in the gradient descent algorithm. The first step is to initialize the coefficients m and b with random values. Now for example, if we take the value of m as 1 and b as 2, then the line equation is y is equal to mx plus b, which becomes y is equal to 1 into x plus 2. Now this can give us a line, but which is not best fitted for the historical data, as you can see from the figure. The line is not best fitted here. So our idea is to find the optimal values for these coefficients that can fit the historic data. Once we find the best fit, we'll use this regression model for prediction. Now the second step is to compute the gradient. For this we use the sum of squared errors SSE as our loss or cost function to minimize the prediction error. Now for this, we find the gradient of SSE, which is the partial derivative of SSE with respect to m and b. The equation for SSE is 1 by 2 into y minus y bar the whole square, where y bar is mx plus b. First, we will find the partial derivative of SSE with respect to m, which is, on substituting, we will get y minus y bar the whole square will become 2y minus y bar. These two will get cancelled, and since the rest are the constants and we are doing this with respect to m, we will get the value as minus of y minus y bar into x. Next, we will take the partial derivative with respect to b, and we get the value as minus of y minus y bar. Finally, the gradient is made up of all the partial derivatives, that is both with respect to m and b, and we arrange them as a vector, which is minus of y minus y bar into x and minus of y minus y bar. Now the third step is to update the coefficients in the direction of optimal m and b. We can update the coefficients m and b using the gradient that is calculated from the equations we saw before. Now the updated rule of coefficient m will be m is equal to m minus r into dou by dou m of SSE, and b will be b minus r into dou by dou b of SSE. Now r here stands for the learning rate. The fourth step is to use the new values of m and b for prediction. We use the data with the new values of m and b computed in the step before to draw the line that will fit the data. Now we calculate the SSE for each data point to find out the total SSE, which is a sum of squared errors of data points divided by 2. Now the total SSE indicates the error rate of the model prediction. So total SSE will be 1 by 2 into sigma I is equal to 1 to n y minus y bar the whole square. Now the fifth step is to repeat the steps 2, 3 and 4. Now this is done until the optimal value for the coefficients m and b are found that will reduce the value of SSE to a minimum. The optimal values of m and b will enable the model to predict y with the highest accuracy. Now the diagram here will show the overall steps of the gradient descent algorithm. Here, computing the gradient of loss function at a specific point in the graph, and then we are updating the weight w, that is the variable of loss function, with the gradient to reach the loss minimum value. Now this is repeated until we are reaching the minimum. After this process is over, we found the best line that fit the data for our regression model using the gradient descent algorithm. Now we'll look into the different types of gradient descent algorithm. We'll start with batch gradient descent. In batch gradient descent, To calculate the gradient of the cost function, we need to sum up all the training examples for each step. That is, for example, if we have 5 million training samples, then the gradient descent algorithm should sum 5 million training examples for each epoch. Now, an epoch is the number of passes of the entire training data set through the machine learning algorithm. So to move a single step, we have to calculate each with 5 million times. So here the updates are done to the model only after all the training samples have been evaluated. Now the model updates and in turn the training speed may become very slow for large data sets. Next is stochastic gradient descent. Now in this one, we use one example or one training sample at each iteration instead of using the whole data set to sum all for each step. This is widely used for larger data set training and computationally faster and can be trained in parallel. We need to randomly shuffle the training examples before using it for calculation. Frequent updates will give an insight into the performance of the model and the rate of improvement, and this is often known as the online machine learning algorithm. Now, the frequent updates can also result in a noisy gradient signal. So, this can make it hard for the algorithm to settle on an error which is minimum for the model. Next is mini batch gradient descent. Now, in this case, it splits the training data set into small batches that can be used to calculate model error and update the model coefficients. The batched updates provide a computationally more efficient process than the stochastic gradient descent. Error information must be accumulated across mini batches of training examples like in batch gradient descent. Now we look into the metrics method for simple linear regression. Let us see a simple linear regression. For example, we need to find the best fit line through a set of data points x1, y1, x2, y2, etc., xn, yn. But what does the best fit mean? If we can find a slope and an intercept for a single line that passes through all the possible data points, then that is the best line. But in most cases, such a line doesn't exist. So we resort to finding such a line when a connecting line is drawn parallel to the y-axis from the data points to the regression line, which measures the error of each data point, that is the sum of all such errors should be minimum. In the diagram given here, you can see these errors are represented by the red, blue, green, yellow and purple line correspondingly. The errors, which is sigma I, is given by yi minus beta 0 plus beta 1 xi. Now our aim is to minimize sigma I squared, which is the least squared. Now to formulate this as a metric solving problem, we will consider this linear equation. Where beta 0 is the intercept and beta is the slope. So beta 0 plus x beta vector is equal to y vector. Now in order to simplify this notation, we will add beta 0 to beta vector. This is done by adding an extra column with 1s in the x matrix and adding an extra variable in the beta vector. We will see that the corresponding form will look like this, with one column of 1s on the left hand side multiplied by beta 0, beta 1, which is y1, etc., yn. Now the least square matrix problem is beta 0 plus beta 1 x1 is close to y1, etc. Beta 0 plus beta 1 xn is close to yn. Now let us look into the initial equation, which was x beta vector is equal to y vector. Now we'll multiply both sides by X transpose, which will give X transpose X beta vector is equal to X transpose Y vector, where X transpose X will be given by multiplying those two matrices. We'll see that on multiplying this row and this column, we see that 1 is multiplied n times. So we write here as n. And on multiplying this row and this column, xi is multiplied n times. So we can write it as sigma xi. The same thing happens here also, which is sigma xi. And here x1 etc. xn is again multiplied by x1 etc. xn. So this will be sigma xi squared. Now X transpose Y vector will be, on substituting the values, we will again see that here y1 etc. yn is multiplied n times. We can write it as sigma y. And here x1 etc. xn is multiplied by y1 etc. yn. So it can be written as sigma xi and yi. Now from the previous equation we discussed, vector beta will be written as X transpose X the whole inverse into X transpose into the Y vector. On expanding the values, we get beta 0, beta 1 is equal to n sigma xi, sigma xi, sigma xi square, the whole inverse sigma y, sigma xi, yi. Now we'll see an example where we take a simple linear regression and apply the method we just discussed now. So here we are having a simple linear regression problem with 4 data points 1, 1, 2, 3, 3, 3 and 4, 5. From it we extract the x and y vectors, which are x vector being 1, 2, 3, 4 and y vector being 1, 3, 3, 5. Now converting it to the matrix form as we discussed before, the matrix will be 1, 1, 1, 2, 1, 3, 1, 4 multiplied by beta 0, beta 1, which will give us 1, 3, 3, 5, which is the y vector. Then we have x vector. So the x transpose will be this. We have the y vector. So x transpose x, we already have the formula we worked out before. On substituting, n will be 4. Since we have 4 data points, sigma of xi will be 1 plus 2, 3 plus 3, 6 plus 4, 10. Again, sigma xi will be 10. Sigma xi square, which is 1 square plus 2 square 4, giving 5, plus 3 square 9, giving 14, plus 4 square 16, which will give us 30. Similarly, we will find out x transpose y vector. We already have the formula sigma y and sigma xi yi. Now sigma y, we will get it as 1 plus 3, 4 plus 3, 7 plus 5, 12, and sigma xi yi as 1 into 1, 1 plus 3 into 2, 6, which will give 7 plus 3 into 3, 9 plus 7, 16 plus 5 into 4, 20 plus 1, we'll get it as 36. Now x transpose x beta vector is equal to x transpose y vector, and we'll substitute the values we got. And on solving the equations, we'll get beta 0 as 0 and beta 1 as 1.2. So from this example, we see that the best line for this model is y is equal to 0 plus 6 by 5, which is 1.2 x. Now we look into the matrix method for multiple linear regression. Now this is similar to the method we discussed for the linear regression, with the 6 steps involved, which are adding a new column beginning with all the ones for intercept in X matrix. Then we are taking the transpose of X matrix, multiplying X transpose and X matrices, finding the inverse of this matrix, multiplying X transpose with Y matrix, and multiplying both the matrices to find the intercept and the coefficients. Now, as an example for this, a data set which contained the price of used car sales from UK was taken from Gaggle, and specifically from it, the first 300 rows from the Volkswagen dataset were taken and only its numerical values were used. And on doing regression using the NumPy in Python, it was seen that the R-square score was 0.77. Now this is the data set, and we have all the values of the metrics here which we calculated before. Now this is multiple linear regression. In simple regression we only had 4 entries. Now here we'll have more entries because multiple regression will have multiple number of linear regressions, and all these values are mentioned here. And in this step they've calculated X transpose X, X transpose Y, Y transpose Y, and X transpose X inverse. And we have the final results. That's all for now. Thank you for watching.